Okay, so yeah, okay. Welcome everyone to this tutorial session for your NPTEL course on Advanced Quantum Mechanics with applications. So I hope you will be tuning to your course because it has already started. First week is underway already, and uh, so yeah. So first week you would have seen some of the topics that is covered by the instructor, and also there will be some assignment problems. I hope you will be going through them. But here we'll try to uh, uh, yeah. So here we will try to uh, look into some relevant problems. Uh, those are essential for your assignment. Those are essential basically to solve your assignments or to understand more about the topic. And yeah, we'll go through some doubts if you have anything regarding the course or the topics that is been taught in your in this NPTEL course. And uh, yeah, apart from that, like if any other issues you are having in the course, you can speak. So okay, if anything you people want to say or ask, you can unmute yourself and can speak. So you people are taking the course, right? So you have registered for the advanced quantum mechanics course, right? You all of you have registered. Uh, okay, yeah, fine. So yeah, we can start with today's topic. Uh, So we'll do basically review of your basic quantum mechanics that I hope you have already uh, are familiar with it. Uh, that is basically the course that is usually taught on your uh, second year of your undergraduate or your graduate program. So probably maybe end of the second year or the start of third year, maybe if I could be wrong. So, but yeah, so that is the basic quantum mechanics course. But now, when you come to this advanced quantum mechanics, it is going to be based on some real uh, important problems regarding physics that is very essential for your, future study. If you still planning to do physics in the future, this is going to be very crucial uh, and also right uh, if you have any other plan, to research to do some research or some other stuff, in physics itself, going forward, then probably this will be very useful, and also from different perspective as well. Like I think there will be topics covering uh, quantum information, and some other nice topics are there, which would be again useful to understand new things about what is going on, modern technology, and yeah, there are many things to follow. So we'll go step by step. And so today is basically the review of basic quantum mechanics, which will talk about some questions that is or you may have seen in some form previously before, and we'll see some of the problems right here. So okay, so, the first problem is about like particle in a box, very standard uh, quantum mechanical system that you always start with. A particle is simple particle which is trapped inside a uh, box, which means like you are trapping the particle basically inside a place where there is no potential, but outside the potential is infinite. So something maybe a quantum particle, a very you can think of maybe an electron or something trapped in some uh, very strong electric field or something. I mean, it has nowhere to go. Like it is something like it, it need not to be necessarily any charged particle, any particle like you are trapping inside a specified region of space where the particle has nowhere to escape. So that is basically the particle in a box system. So in a right, a particle of mass m in an infinite square well potential. So this is your potential. So potential is zero for a certain reason, that is 0 to L. So you are considering only one dimensional system. So if it would have been three dimensional system, you would have you can say that a region exists like a cube. I mean, I could have said that for three dimension, the that region could be 0 to L in one dimension, which is x, and also in y direction you have 0 to L restricted region, and z direction. So three directions, you say that the potential is zero and the particle is trapped right there. So that means in a cubical region your particle is trapped. So it did not to be cubical, it can be anything spherical or could be any random reason, but this will provide us like more useful advantage to solve the problem, right? So and still we are considering one dimensional system, and outside the potential is infinite, so it is like that. So for one dimension I can show along x, you have the region 0 to L. Between 0 to L you have potential 0, and then uh, outside this region you have infinite potential. So if a particle is trapped right here, so it cannot escape from this way or neither from this way. So it is completely blocked. So so this is a very familiar system. So right. So a particle is trapped under this potential, and it is in the following state. So is the particle is trapped inside this potential and is prepared in a state with the wave function this. So what is this wave function? So this wave function, I mean, you would be aware of some like eigenstates, eigenwave functions. So it doesn't look like exactly like eigenwave function, because for infinite well, if you would recall, the eigenwave functions go something like this. Uh, uh, Something sine. There will be. I mean, so for let me write here just a small recall. Eigenfunctions of 1D particle in a box, uh, that goes something as psi n. If I represent the each n as distinct eigenstates, then it was something to 2L sine n by x by L. So yeah, right. So this was your eigenstate of your 1D wave, 1D particle in a box. Okay, so but this doesn't look like that eigenstate, because you see there is cube here. So this cube basically is spoiling the. I mean, basically this cube is the one by which you cannot say exactly this is eigenstate, but we'll see. But so I hope you would be aware that if eigenstate is not possible for a quantum particle to be, if quantum particle doesn't seems to exist in eigenstate, then the other possible way is to be that particle could be in some other state, which we know that they are linear combination of many other eigenstates. So yeah, so it could be that. So that means right here. So then, if that is your problem, then calculate the expectation value of the energy of the particle. So if the particle is given in this state, then what will be your expectation value of energy? So right. So okay. So that was a question. So now, so as I said, like, let me begin again with uh, the eigenfunction, the nth eigenfunction. Uh, I can write it as psi n x root square root 2 over L sine n by x, then L. Right. So your particle is this function basically goes from 0 to L. So this you would have must seen that I mean in your uh, previous course of quantum mechanics, like you would have also derived this, and it is 0 uh, if yeah, the otherwise outside L greater than x greater than L, or uh, x less than 0 is also the reason where you will not see the particle to be exist. I mean, the particle cannot escape into these reasons. One is x greater than n, and the other is x less than 0. So, so now the given state is psi x a sine q by x over n. So that is your state, which is given in a question. So now let's see if you remember the relation for sine cube theta in terms of linear sine theta. So what I mean. So if you remember this relation, sine 3 theta is basically 3 sine theta uh, minus 4 sine squared uh, theta. So not this is 4 sine cube theta. Yeah. So from here I can write what? I can write sine cube theta equals to 3 over 4 sine theta minus 1 over 4 sine theta, sine 3 theta. So using that, I can write my given wave function is 3a over 4 sine pi x over L, then minus a over 4 sine 3 pi x over L. Uh, yeah. Now, yeah, I forgot to mention here, and I hope you know that this n, which is here, so this n goes as 1, 2, 3, and so on. So each n denotes each distinct energy eigenstate. So, so now you can see some correlation right here, or rather, yeah. So from here you can first thing which you can guess is here. So this is a given psi is your linear combination of eigenstates, some linear combination, because you see there are uh, um, so if you see each term, suppose the first term, you see the sine pi x L is something similar. Here you can find if you put n equals to 1, then that will give you sine pi x L. And for the second term, you see here, this is sine 3 pi x over L. So if you put n equals to 3, that will give you sine 3 pi x over L. So this means it is a linear combination of your energy states. So it is a linear combination of energy states. So right. So uh, yeah, I can write this as your n equal to 1, n equal to 1 eigenstate, and this is your n equal to 3 eigenstate. Okay. So now, so you figured out what is your uh, wave function, what is your given state of your particle which is trapped in a 1D potential. So then your next task is to compute expectation value for the energy. So how you will do that? So now see. Uh, uh, so to compute expectation value for energy, uh, you have to compute something following. Uh, yeah, so this psi is your given state, which is given in a question. So which we figured out, it is a linear combination of first and third energy against it, and so if you want to compute the expectation value of energy, then you will take the expectation value of Hamilton H of your system. So I hope this is how you take the expectation value in quantum mechanics. So you take it, for example, you want the expectation value of momentum. Uh, so then you take momentum operator, and then you sandwich that momentum operator in whichever state you want to compute the expectation value. So that is how you do. So right. Then but suppose if I would have some given state would have been something, let's say psi 2, something sine uh, 2 pi x over L, then expectation value of energy would be psi 2 h psi 2. Then you would have calculated uh, h means your Hamiltonian. So your Hamiltonian goes something minus h square by 2m del square by lx square plus, and there's potential, and then you use sine 2 pi xl, and then you calculate this Hamiltonian. So that way you would have done that. But now you don't have any psi 2 or psi 3. You don't have either psi 2 or psi 3 or psi 1. You have linear combination of both psi 1 and psi 3. So for that, yeah, for right. Uh, So if you have psi as some linear combination of uh, phi 1 plus phi 2, phi 3, and so on, then let's say do some psi and phi. So your phi 1, yeah, let me denote this as phi, otherwise there will be a slight confusion in notation. So let me denote this as phi. Yeah, that's okay. Uh, so right. So these are your eigenstates. This phi is your eigenstates. This phi n's are your eigenstates. So if your given state is some linear combination of eigenstates, so let me say again here. Here phi one, phi two, phi eigenstates. Then you can calculate your expectation energy as summation I, where I is the index that sums over like here in this way. So there was a question, I guess. Yeah, is this let me is this mixed state is normalized, or how to check this? Yeah, so first of all, like by mixed state means this is not something you will call this as mixed state. So mixed state is something you would probably learn it. I mean, in this course itself. So like I think it will be in around week 3 or week 4. You will get to know what is mixed state and what is pure state. So they are different things. So what we are dealing here are pure states. But you can call this a psi as linear combination of other states, linear combination of eigenstates altogether, which is completely a pure, I mean pure state. So in mixed state, like there will be like entanglements and other things that you will get to know. So uh, so this is not mixed state, and so this is your linear psi is some linear combination of states, which is not your eigenstate, right, of course, but your phi 1 phi 2 individually they are eigenstates. And if you want to see if the state is normalized or not, then you can just simply take the inner product of this psi. So that is how we do. So psi uh, this is the inner product of psi. Inner product square has to be 1. So this gives your probability. So this is your total probability. So or otherwise I can write this as something psi conjugate psi dx. And so if you are dealing with one dimensional system, so this is how it will be. So, and this has to be 1. So this is your normalization condition. So if you think that this is not this psi this mod psi square is not equals to 1, then that psi is has to be not I mean uh, not necessarily be normalized, but there will be some factor by which you can make it normalized, overall factor. So unless you don't know what are the explicit values of C1, C2, C3, you cannot tell it as a normalized state just by looking at it. I mean, or if there is some non-condition, you can say. But yeah, uh, C1, C2 has to take some value such that this, if when you do this inner product, then this will give 1. So, is that your question, or anything more you wanted to? Anything? Okay, fine. So, if you have anything more, you can ask. You can simply turn on your mic and speak. Yeah, fine. So I was telling. Okay. Yeah, I was telling, if you want to calculate the expectation energy uh, for your, state, which is, I mean, uh, in some linear combination of eigenstates. So, because as I said, the expectation value you calculate under some state in quantum mechanics. So, if your state psi is not eigenstate, then you cannot just simply, operate the Hamiltonian on the eigenstate. I mean, if it is a linear combination, you have to operate on its individual terms. So, through that process only, you can end up a very useful relation, which you can use it here. So uh, that I was telling you right here. So this is this. So, so what is CI? So this CI are basically this C1, C2, C3. They are otherwise, I think, known as uh, transition amplitudes or coefficient expansion. Yeah, expansion coefficients or transition amplitudes, which you can say. and let me say expansion coefficients or transition amplitudes, or so yeah. And uh, this lambda I gives you the uh, eigenvalue or energy, in this case energy eigenvalue. Okay, then right. So if you take this ci as modulus squared, then that gives the probability of uh, yeah. Let me denote this ISN because I was already denoting it as uh, N before. So it's just a small notation change. So here I was denoting N. So that fine. Yeah. So these are your N. Probability of particle to be in the nth state, nth eigenstate. So, so this is your relation through which you can get your answer for your expectation value of energy. Okay. So yeah, I can write here. So like to know exactly how this happens, I can show you quickly right here. So you have, I mean, you want to know expectation value of energy, then as I said, you have to do psi h psi. So that is, uh, yeah, you can write psi uh, get psi as C1 star. You have to take the complex conjugate, uh, phi 1 plus then uh, C2 star, then phi 2, then so on. Yeah, this way you can write this quickly. C1 star phi 1 plus C2 star phi 2 plus so on plus Cn star Cn star phi n. Then you have H, and then same way you have C1 phi 1 plus C2 phi 2 Cn phi 1. So this way you can finally write here. You will see that you will use the idea that phi and phi n are phi n, all the phi 1, phi 2, phi 3, they are your eigenstates. So that means, so each of them are orthogonal to each other. So psi and psi m, if you take the inner product, then it will be delta function, or basically Kronecker delta, which what we call. So if n and m are not equal, if n is equals to 2 and m equals to 3, then phi 1, phi 3, if you take the inner product, so that means that you will end up with 0. They are not equal. So right. So if n and m are equal, so phi 1 and phi 1, you are taking inner product of itself, so then it is 1. If it is normalized, it will give you 1. If it is not normalized, then you'll find some non-zero value, so some positive non-zero value. So yeah, this way you can write, using this you can write the, so you will find this phi 1 when so first h will act on phi 1, so that will give you when h acts on phi 1. So let me say, so from here you will get h phi 1 will basically give you lambda 1 phi 1. Lambda 1 is some eigenvalue corresponding to phi 1. It is the energy eigenvalue, because phi 1, phi 2 are the energy eigenstate. So energy eigenstate, then that means it should follow this relation. Uh, H phi 1 equals to lambda phi 1. So simple energy, simply eigenvalue equation. So right. So in general, you can write this H when x on phi n. It will give you lambda and phi n. So yeah, from here you finally have uh, c1 square lambda 1 plus c2 square. So yeah, so how this is going, let me tell you. Cn square lambda, yeah. So after after when you get this right here, so from the left hand side you have another phi 1 phi 2, all this factor is there. I mean the total factor is there on your right hand side. Then on your left hand side. So then this, each of this term will again act on this phi one. So so you can check this out. First, when h acts on first term, it will give you lambda one phi one with c1 multiplied, and then again from your left side you have this factor. When you will see first, when phi 1, this phi 1 again acts on this phi, uh, when this phi 1 acts on this phi 1, it will give you 1 if they are normalized. So let us assume that they are normalized. So if they are normalized, then c1 and uh, uh, c1 star and c1, when they multiplied, that is magnitude square. So there was one question. So if you are telling I mean, if this I mean, there was one question from someone who was basically asking whether psi is normalized or not. So this psi, you cannot I mean, I said to see if psi is normalized or not, you basically have to like compute c1 and c2 and c. But here I am telling whether phi 1 phi 2, they are individually normalized. So here I'm assuming they are individually normalized, because if you see, if I'm calling phi as this, uh, this is my phi, then if you calculate phi 1 star phi 1 and you integrate over dx, you will find this will be 1 from 0 to L. So, and if you calculate phi 1 star phi 2, then integrate it, you will find it 0. So yeah, yeah. So this is my phi 1. These are my eigenstates. Yeah. So here the individually each phi are normalized. So from here, yeah, you can get this. Uh, so after, when you get this lambda one phi one, when phi one acts, then phi one keeps you one. If when phi two will act, it will be 0. So then, so there is no c2 star c1. Likewise, there is no c3 star c1, and no other such terms. So you only find c1 star c1. Likewise, when you will find h1 acts on phi 2, you will get lambda 2 phi 2, and from left this left hand side factor, again when phi 1 will multiply, it will give you 0. But when this uh, graph phi 2 will act, that will give you 1 phi 2, I mean phi 2 phi 2 inner product is one. So yeah, so this is the relation I was talking about. So that is I yeah, I was denoting n. So Cn mod square lambda. So that was relation. So now I can quickly calculate the energy for the given question. So the state I was calculating in state psi. So so the state psi is this one. So this is our psi psi x. So you see that it is linear combination of two states. It is this is psi one, or basically this is phi one, and this is phi three, because you see there is a three factor inside the argument of sign. So because that is what n here denotes the nth eigenstate. So this is your third eigenstate, and this is your second eigenstate. This is your ground state. That is how you conventionally know. So yeah, so you have phi one and phi three, and besides you have factor. Uh, this is your C one. Right. So yeah, this is your C one, and this is your C two. Yeah. So there was one question. Phi, so why phi three instead of phi two? Uh, no, it will be phi three, because here you see. Um, So in the given question, you have the state in which the particle is existing is this a sine cube pi x over n. So from here you cannot say that, first of all, it is definitely not your eigenstate. So it would be probably in some linear combination of state. So, and that you will get if you re-express this sine cube pi x over n. So to re-express that, so I used this relation. So this relation sine 3 theta equals to 3 sine theta minus 4 sine cube theta. So this is your some trigonometry relation which you can get it if you search around. So this is your simply a trigonometry relation, and from this trigonometry relation, I can write sine cube theta as 3 by 4 sine theta minus 1 by 4 sine 3 theta. So you see this 3 is appearing. So same way, if I do a sine cube pi x over L, if I rewrite it, then I will get 3a sine pi x over L and a by 4 sine 3 pi x over L. So that is why I get 3 here, not I will get 2, because from this relation that is how it is coming. So there is no 2 theta appearing in this relation. So the relation between sine cube theta and sine 3 theta. So so that is what your uh, question was. Or so is it clear, or uh, I think devil jets. Uh, was that your like? Was that answered? Okay, yeah, fine. Yeah. So I was calculating an expression value for the energy for the given state which is in. So we found phi one and phi three are the eigenstate in which your uh, particle is trapped inside the 1D potential. So from this relation, I can write C1. I found C1 is 3a by 4. So magnitude square. So 3a by 4. So this is itself is a real number. I can take simple square. Then lambda 1. So lambda 1 is your, let me write as E1 is the eigenvalue for the infinite well ground state, and plus you have the second you have this is a okay, probably you would have confused with this thing. So this I should have written this as C3. Okay, probably like my bad. That is incorrect notation. So yeah, yeah. Sorry. Yeah, so this would have been C3. Not so. You might have confused with this that this would have also been 5 2. Yeah, but yeah, this will not be 5 2, but this is 5 3. But this is C3. So yeah. So the C2 is not here because there is no phi 2. So yeah, fine. So then C3 mod square. So C3 magnitude square will be this is minus a by 4. So you will have plus a square by 60 plus a square by 60 E3. So now what are E1, E3? So eigen values for infinite value En for so yeah, En is or let me write somewhere. Okay, fine. So En is n square pi square h bar square over 2 m l square. M is the mass of the particle and h bar, this is your Planck's constant, right? So L is the length of the particle box. Uh, so you have E1 and E3. So if you put that, you will get uh, yeah. So yeah, that is what your answer is itself. So pi square h bar square over 2m l square plus a square over 16. Then E3, that means 3 square 9 pi square h bar square 2m l square. So that is your expectation. So if there is any doubt over here, anything you wanted to ask, like you can ask now. Anything you missed or something here or you couldn't understand properly. Yeah. Okay. Ask. Mm. Is there any doubt? We can assume E2 is zip. Yeah, I mean, you see, like in the question, like it was only given a sine cube pi x over l. So that means if I rewrite in terms of linear terms of sine, so sine cube, I'm writing sine cube as sine theta and sine 3 theta. So there is, you see there like there are no sine 2 theta, sine 5 theta. There are no sine 6 theta or whatever. So there are no other terms. So you only get sine theta and sine 3 theta. So again, so when you re-express the sine cube pi x over l, so you will write only sine pi x by l and sine 3 pi x over 3 pi x over l from this relation. So so and that's it. Only two terms are there. There are no corresponding terms to sine 2 pi xl, sine 5 pi xl or 6 pi xl. So all these terms are not existing here. So that means there will be definitely no C2, C5, C6. So they don't exist. So yeah, they would be zero. So here you have only two eigenstates, phi 1 and phi 3. So corresponding to phi 1 you will have C1 and corresponding to phi 3 you have C3. So there are no C2, C5. Okay, fine. Yeah. Any more question or any other doubt you can ask? Uh, You can tell, like you can ask any doubt, like any small thing you missed or any like whatever, like it is not properly something like you unable to follow or okay. So if there's no more question from here, then we can move ahead. Uh, right. Uh, so another similar question. So let me complete the question first. So uh, okay. So a particle in the infinite potential line again we have. So this time the size of the 1D potential is again of length L, but here it varies from minus L by 2 L by 2. So earlier it was from 0 to L. Is prepared in this state with the waveform. This is your initial. This is your given state, phi 1 and phi 3. Again here you have 5 1 5 3. Here 5 1 and 5 3 are normalized. So here it is properly specified. It is normalized. I should have also specified before in the first question, but yeah. So uh, these are your ground and second excited state, respectively. Calculate the following. So first question would be the shortest time t after which the state will repeat itself. Okay. So what does it says? Like I mean, suppose I mean, uh, so you have some psi t0, that is your initial step. So let me write so psi x t equals to 0 is your initial state, which is equals to half phi 1x plus I 3 by 2 phi 3x. So now, uh, like uh, yeah. So there is one more thing. Suppose like if you are evolving any energy against it, like for example, the as I said before in the before question that phi n are your energy against states. If you are calling this phi n is your if you're calling these phi n's are your energy against state for the 1D potential well, then uh, and these are your eigenstates for your for your Hamiltonian operator H operator. So if that is so, you will find they also that means phi n should be something like this. So which we also used in our previous question. So this is your eigenvalue equation. So that means your phi n are the eigenstates of operator H. So then uh, you can so when you if phi n, let's say phi and t equals to 0 is let's say is phi 0 or how should I let's just simply I write phi n uh, and then phi n at t equal to t prime it will be something phi n prime. So, or yeah, phi n prime. Like, yeah, you can write this. So that means you are starting with some state like your quantum particle, as we saw in the previous, as we show. I mean, in the previous question where it was trapped in a 1D potential wave. So that particle initially had some state, say phi one, like some eigenstate it was. So then you left that system as it is, then it will evolve under time. So its probability distribution will change basically. So I mean the total probability has to conserve. There is no other I mean other interference from outside, then the probability should remain conserved. I mean there is no dissipation or decay of states. So I mean simply just consider that there exists only one particle with its one of the eigenstate, five, let's say phi one. Then if you leave that phi one as it is, then it will evolve under time. So after time t prime, you will see that phi would have changed. So how we can write that? You will use evolution operator. So evolution operator, how you write? So phi and t of t prime, I can write as u of t phi n. So that means you operate uh, u on phi, uh, then it will evolve to some t prime. So that means this will be t prime. Okay, I can write it as exponential minus I or h bar uh, en, not h bar, uh, phi n. So this is your evolution operator. So this is how you write your evolution operator. So from here you can see, uh, right. So here you can write, or let me write here. So I can write this as minus I over h bar en t phi n. Uh, Here you can see this when h acts on this phi n, it gives, say, uh, en phi n. So earlier, which I was calling lambda n, or that I'm denoting as en again. So because I mean uh, it goes I mean fine with this eigenvalue notation which we write, because eigenvalue in general you can denote as lambda, but here I am specifically dealing with energy eigenvalue, Hamiltonian eigenvalue. So I can write that lambda is en. So or you can write it as lambda n also, no problem. So minus I over h bar lambda and t. So this is the idea. I mean this is how you evolve your system. So when you will evolve, you will see that your state will pick a phase. This is basically overall phase. And so you will see that like I mean it basically your state will change by some amount of phase, but overall the total probability has to remain the total state. I mean the total inner product of the state will be conserved. So if you take the inner product like something phi n t prime phi n t equal to t prime, you will find I mean if this phi n are normalized, then you will get 1. If it is not normalized also, you will get some non-zero positive number if you take this square. And then you also compute phi n at t equals to 0, and also phi n t equals to 0, this inner product, this will be also give you the same value as this one. So that means your total probability is concept. So there is no issue with that. So right. So yeah, then we can move on. Which here what we need to focus about is uh, yeah, as a different. This is our given initial state. This is your initial state. So your let's say after when you evolve your initial state to some x and t equals to t prime. So that means you can again write exponential minus I bar h bar, Hamiltonian operator, then t prime. Yeah, t prime. It will be t prime here, t prime. Right. So this will be psi x t equals to 0. Uh, yeah, you see this phi n is your t equals to 0 state. This phi n. This phi n is your t equals to 0 initial state. So yeah, so likewise we have psi x t equals to 0 is this initial state. Then at t equals to t prime, you can do this operation again. So this is your evolution operator u of t, right? So you can write psi x t equals to t prime, uh, h bar, uh, Hamiltonian operator t prime. Then psi xt0, you use what is given in the question, phi 1x plus I root 3 over 2 phi 3x. Then remember this is your operator. So when this acts on this phi 1, so using this idea which I just showed right here, so this will give you uh, exponential I h bar e n t prime, then phi n. Similarly, here also you get uh, 1 by 2 is your overall factor of your first term. Then when this exponential, when this evolution operator acts on phi 1, that will give you uh, exponential minus I1 h bar E1 t, then phi 1, right? Then plus uh, similarly you will do with the second term I root 3 over t, then exponential uh, I uh, yeah uh, I over h bar e3 t. So remember this. This is again I'm forgetting to use t prime. So yeah, I mean at t prime you are evolving. So yeah, this is your state when you evolve your system to t prime. Then what will happen? So your question was basically what is the shortest time after which the state will repeat itself. So if you call at t equal to t prime, this is your state. Uh, this is your state at t equal to t prime. Uh, is your psi at t equal to t prime, and your psi at t equals to t0 is this one. That means you want this state psi equal to t, psi at t equal to 0. You want this state again after evolving some time. Let's say when you evolve some 2t prime or 3t prime or something, t prime plus delta t or something. So after when you equal to, let's say, some t double prime, you will find this psi c. I'm saying c is x t equal to double prime. This will be same as psi x t equal to 0. So it will repeat itself to its. It will go back to its original state. So that means you have uh, right. uh, what I'm saying, you want psi x t equal to t prime. Let's say that this is at that time. I'm assuming t equal to t prime is that time where it will be equal to its initial state. So this is equal to the initial state. So if that is so, I can, how I can write that? Let's say I can write the same thing back again. That is psi x t equal to t prime. uh, Here you see, if I take a overall factor of this phase from both the terms, then what I will get, and you will know why I'm doing this. E1 h bar t prime, if I'm taking this as common, then first term I will left with half of I1. Then in the second term I will have square root 3 over t with iota. Then uh, yeah, this will be minus the lesson was there previously. So this is minus I E3 minus E1 red over H bar T uh, T prime phi 3. So this is what we will have after when I take this common factor. So what I'm doing here, I'm taking, because both of them has some phase multiplied to each individual eigenstates. So I'm taking the common phase out of them. So if you how that will help, because if I take this psi x t, t equal to t prime. Let's say if I remove this phase, then nothing will, I mean, bother me about this state particular. Because if I have this state, what does this means? Like if I do psi x t prime and psi x t prime, uh, including this factor or including or excluding this factor, I will get the same result. So the I mean, I will not find any change in the probability for this psi. So I can take this factor over. You can ignore this overall factor as it will not change the probability distribution at psi for psi x t prime. Yeah. So that means I can write my psi equal to t prime. So this is just simply like, I mean, whatever phase you have, I'm calling inside whatever is my psi at t prime. So this phase will not matter, like, because when you take inner product, so minus I phi I phi, so they cancel. So that is why. So you can ignore this phase. Then uh, yeah, so that means I can write my eigenstated equal to t prime is uh, copy this. So this is my psi t prime state. So I have to now, for as I said, there was this claim that at t equal to t prime, if my psi is same as t equals to 0, then I can equate this psi, both the psi, in the like following way. I mean, uh, yeah. So when you will equate this psi t prime and so as I was telling, so when you equate this psi t prime with psi equals to 0, or let me just open t equal to t prime and t equals to 0, then you see the first term in both of them are same, half of phi 1, and here also you have half of phi 1. In the second term you have I square root 3 over 2 phi 3, which you also have at t equal to t prime, I square root 3 over 2 and phi 3, and you see only this is your different factor in the second term. So now this factor has to go 1 in order to have this condition. In order to achieve this condition, you have to make this factor to go 1. So that means exponential minus I e3 minus e2 over h bar d prime is 1. So and 1 I can write is like from Euler's relation, from this exponential relation you have idea about. Uh, we can You can write this any um, I mean exponential e to the power iota as 1 if it is iota minus I 2 m pi, or there is minus I 2m plus 1 pi, then it is minus 1. So where m goes as 0, 1, 2, 3. So if you put m equals to 0, then that is e to the power 0, that is 1. If you put uh, m equals to 1, that means e to the power I2 pi. So e to the power I2 pi means that is basically you write e I theta as cos theta plus I sin theta. So uh, yeah, there was some question. Okay.
Sir,
Yeah.
I think you did a mistake, sir.
Sorry.
The E3 minus E2.
Uh, E3 minus uh, it
E
will
minus E1 होगा sir.
sorry, what is wrong? E1 is not
Sir,
uh,
in exponent term sir, आखिरी में
uh,
वहाँ पे
हाँ.
E3 minus E2 लिखा हुआ है. E3 minus E1 होगा sir.
Okay, okay, yeah, yeah, yeah. So thanks. So you are telling this E वाला term बोल रहे E3 minus E1.
Yes sir.
Okay, okay, yeah, yeah. Okay, so now it is correct, right? E3 minus E1. Okay, so yeah, there was a typo. That is not 2, that is 1 actually. That is E1. Then E I theta equals to cos theta plus I sin theta, which you know. So from there you can see if theta is 2 pi, that is basically 1. So I'm saying this that you can because we have to make this. e to the power I, this entire thing inside, uh, equals to 1. So that means we can write, uh, so so this is what we have so far with us. Then uh, yeah, so I can write this as uh, or basically I can write E3 minus E1 over h bar t prime equals to 2m pi. So 2m pi, and this whole thing. So yeah, that means I can write t prime as 2m pi h bar over E3 minus E1. So now you finally got the time where you will achieve, or otherwise I can write t prime as 0. That means that is the initial time. So initial time obviously will be the same state what you started with the, or what we have the state. So that is the initial t prime. So or that is something not very much meaningless. So I mean, it is that is not very much meaningful in the sense, like, because t prime equals to 0 is your initial time. So because you want some t prime after you evolve your system from t0, then that time will be something where your state again achieves your initial state. So this is this time. So when, if you take m equals to 0, so that is not worthful. But if you take m equals to 1, then that is 2 pi h bar e3 minus e1. At this time you will find yours, so if you calculate psi at t equals to 2 pi h bar over e3 minus e1, you will exactly find your psi to be the initial psi. So you put in here as we show somewhere, yeah, so here, so you put this t prime in this expression. So in this expression, you put the t prime, what we got, that is 2 pi by this thing, 2 pi by e3 minus e1. Then you will get the same state as we started. Or you will also have other time, that is 4 pi h bar over e3 minus e1. If you take m equals to 2, so m equals to 1 is 2 pi h bar or e3 minus e1, and yeah, so on you can take, because here m goes 0, 1, 2, 3, so on. So these are your time where you will get the same step back. So yeah. So again, anything, any problem, uh, you can ask. So any questions? Okay, anything you didn't understand, or anything you missed during this discussion? Something very not clear, something small or big? No problem. You can.
सर
Yeah, yeah.
सर ये एक्सपोनेंट टर्म से E3 माइनस E1 अपॉन एच का टेन टी डैश इक्वल टू 2m पाई, ये यहाँ कैसे पहुंच गए सर?
Uh, uh,
सर एक्सपोनेंट टर्म से या सर यहाँ पर
this will ये रिलेशन की बात कर रहे हैं.
ये थोड़ा सा नीचे से।
This one.
हाँ सर, ये दोनों।
ये.
हाँ, ये और इसके ऊपर वाला।
हाँ. आपको ये समझ में आया, मतलब.
ये समझ में आया सर। सर
So,
यहाँ से ये नीचे वाला कैसे आया सर,
हाँ,
ये
हाँ,
वाला?
हाँ. तो मतलब मैं इधर से इसी रिलेशन से ही बोल रहा था, लाइक व्हाट आई वाज टेलिंग. So if you have this, because this is what you want to make your state at t prime to be the initial state, you have to make this condition. Your exponential of this has to be 1. Then I'm saying anything which is exponential of minus I 2m pi, uh, that is also equals to 1. If you take m equals to 0, 1, 2, 3, whatever, so on, if you go on like this, because you can check this, if you what does ei theta means? It means basically cos theta plus I sine theta, right? This is your Euler's relation. So from there you can see always cos 2m pi plus I sine 2m pi. This will always give you 1 irrespective of m 0 1 2 3, m being 0 1 2 3. So take m 0 1 2 3, whatever you will get, uh, 1 always, because this cos of this thing is 1 and the sine of this is 0. So that is why e to the power minus I 2 m pi is 1. uh, then that means I can equate e to the power this thing, because I want also this thing to be 1. So I can equate minus I e3 minus e1 over h bar t prime equals to e to the power minus I 2m pi. So that means this has to be same. So E3 minus E1 or H bar T prime equals to 2m pi. So this is your 2, this so T prime is 2m pi over 2m pi H bar over E3 minus E1. So now is it clear, or
Yes, yes, it is.
पता चल समझ में आया, right?
Yes, yes,
Okay,
it's clear.
okay. So yeah, any other question, anything? Uh,
No, sir.
uh, okay, okay. Then we can move on with the next uh, uh, question. So in this same question there is another part. So let me write down. So this was the first part. So second we have uh, the uh, you have to find the uncertainty in the energy of the particle in the given state. So uncertainty of the particle in the given state. So uncertainty means like you have I mean so basically it is the standard deviation. So what does I mean or you have to calculate uncertainty in energy. So uncertainty in energy, that means you have to calculate delta E, which means square root of E square. uh, yeah, so you have to calculate the average of or the mean value of E square minus uh, yeah, mean value of E squared. Then the whole thing is taken under the square root. So this is your standard deviation. That is basically your definition of uncertainty. So so as I said, like before, this, already, like which we calculated just in the previous question. So the one before we solved the last one. So that is, as I as I referred earlier, if you calculate you want to calculate any expectation value of the, or basically the expectation value of energy, then you can calculate using this relation, n lambda n c n square. Or so that means, yeah, so this is your definition for your expectation value of energy. This is the relation with which we solved in the last question. Then same way, so you just have to take the square, because that is what you need here. And then next, same way you can also do this. This is also, like, you can prove this way in the same way we did it at the beginning. So I'm telling you can calculate e square average also, summation and lambda n square c n square. So now you know both of these. I mean, how to calculate. So they are not very different. So just how you calculate mean energy, you calculate mean of e square, mean of energy square. So mean energy we can calculate again. So you see, we just need, we have uh, two states here as well. So as you know, C1 and E1 plus, so this will be C1 square E1. So your lambda is basically E1, E2, E3, or lambda 1, lambda 2. I'm denoting as E1, E2, E3. So which I have told you before also. So then we have C3 square E3. So now what are they? So uh, but variance in H is zero, I think. Like, how it is zero? This is uh, variance or standard deviation. Okay, standard deviation is not, or variance is not zero. If it is your eigenstate, let's say, uh, you have, if I'm telling psi 1 equals to phi 1, the eigenstate of, or the ground state of the infinite way. If I'm telling uh, if I'm telling psi is equals to phi 1, if I'm telling psi or phi 2, phi 3, whatever, then in that case you have sine pi x over L. So that is your uh, phi 1. So in this case, if you calculate energy, so corresponding to this phi 1, the energy will be the eigenstate, eigenvalue, that is I square h bar square over 2 mml square. This will always remain same. So if you are given with any eigenstate, then corresponding to that eigenstate, the standard deviation, the uncertainty is always zero, because that energy is fixed. But if you are given some linear combination phi 1, phi 2, phi 3 with some factors c1, c2 plus c3, phi 3, and so on, then in that case, uh, you have to calculate expectation energy, which is different. And also you will find e square expectation, which is also again different. But in this case, e and uh, you take e square, I mean expectation square, then e square expectation, they are both same. They are both same. But here it is not. When you have psi, so if you have linear combination of states as your defined initial configuration, uh, then your then your uncertainty is not zero. It is zero if you have only eigenstate. But here you
Okay, sir.
linear combination. Okay. So you got the point, right?
Yes, yes.
Okay. Yeah. So that means you have to calculate this main energy, this expectation. So, and this is equals to, you see, C1 is what was C1 given in the question. So C1 is basically half, and C3 is I root 3 over 2. So if you take C1's mod square or magnitude square, that is 1 by 4 E1, and E1 is, as I just wrote, moments back. It is pi square h bar square 2 ml square. Then plus uh, I C3 magnitude square. So C3 is I square root 3 over 2. That is 3 over 4. 3 over 4. And E3 is 9 pi square h bar square 2 ml square. So this is your expectation value of your energy. Then you take E square expectation. Then that will be you will use this relation. Then again you have 1 over 4. Then instead of pi square s square square by 2 ml square, just you have to square it now. 3 by 4 and pi square s bar square 2 ml square. Square them, and then you do this. Uh, yeah, then you just have to calculate this. Yeah, you can do that. That is just simple computation, and from there you take square root. That will give you uncertainty. So this is your uncertainty uncertainty energy. Okay. Uh, Fine. Then yeah, is there any question right here in this part?
No, sir.
Okay. Anyone else? If have any problem in understanding anything, like if you missed anything somewhere, like you can ask. So if not, we can move with another question. So that is related with another system, which is again another standard system used in quantum mechanics, which is harmonic oscillator. So let's see what it is. Um, Consider, yeah, okay. Consider the normalized state psi of a particle in a linear harmonic oscillator where psi equals to T1 0 plus T2 1, where ground first excited. So you have a quantum harmonic oscillator system where a state is given, which is in ground and first excited state, a linear combination of ground and first excited state. So then, if that is so, then again you calculate the expectation value. What is the uh, right? expectation values of the displacement x in the state sign. So, and there is given operator. You use the operator given x operator is h bar 2m omega a plus a delta. So this is your given operator. So using this operator, you calculate the so m is the mass of the particle, omega is the frequency of the harmonic oscillator. Uh, so, uh, so this is your position operator. So using this position operator, you can calculate what how much I mean how much your system is displaced from its mean position in this oscillator state, which is psi. So uh, so again we'll do the same thing. So again, what we need for expectation, for if you want to calculate expectation, that means we have to do this psi. uh, so psi is given to be d1 0 plus d2 0 d2 1, then conjugate of psi is d1 star 0 plus d2 star 1. Yeah, so I can now use this in the expectation. Yeah, d1 star 0 uh, plus d2 star 1, d1 0 plus d2 1. Now, so here you can see, uh, yeah. So yeah, you have to evaluate this x operator acting on ground state and also on the first excited state. So as we saw before, like how we were operating Hamilton operator on the ground state for the 1D infinite way, the same way you have to do. In this case, you have to operate X operator. So for how does this X operator act? So we have this X operator given as sum of A and A daggers. So A and A daggers are creation and annihilation operators, which are like defined in harmonic oscillator systems. So this A operator means that is what we call creation operator. By meaning it does basically uh, I mean it does the task of taking your particle state to one step above. So like if you are in ground state, if the particle is in ground state, then if you operate this A operator, the sorry, let's say if you are in second excited state, and if you operate this A operator, it will bring down. It will. I said initially incorrect. Like so, it the A trigger will take you the one state above the one it was there before. So, so I can write it as so for in quantum harmonic oscillator phi n is your eigenstate. So this eigenstate you can write it as a, it is alpha n square x square. So I'm not going into this details of eigenstate. So uh, you can refer to any standard text of quantum mechanics to know in more detail. So you have hopefully seen this in your first quantum mechanics course. So just a review that I'm doing to recall you what are the eigenstates and what are uh, creation and annihilation operator. So if I write creation operator, the A dagger operator, yeah, A dagger operator, I can so n is your nth eigenstate. So here as we were denoting zero first, so ground eigenstate, first excited state, second state. So if when a dagger acts on the nth state, it will take you to n plus 1 state with a prefactor n plus 1. So remember, this is not a eigenvalue equation, and this if you operate a on nth state, then it will take you to n minus 1 state. So basically you operate, then it takes you to n plus 1 if you have a dagger. And if you operate n, then it will take you n minus 1. So it will lower the state of the particle. So now you got the idea how this a dagger and a acts on the eigenstate. Using them you can calculate the expectation as follows. So now you can directly write down. So use this operator expression. So that will give you something. Let me write all the terms. The terms that you will get: b1 square, uh, then there will be another b1 b2 cross term, that will be 0 x power 1. Then similarly you have uh, b1 b2 1 x 0, then plus b2 square 1. So yeah, now you use the operator, the form of operator form of x which is given in the question, so that from there you have order factor of h bar 2m omega square root to from b1 square 0 a plus a dagger plus, sorry, a operator plus a dagger operator, then your b1 b2 uh, a and a dagger operator acting on 1. Then you have uh, yeah, b1 b2 again you have 1 0 plus b2 square 1 a dagger 1. So right here. So yeah, so from here you see you can first you can look at the first term. So when a dagger acts on 0, it will take you to 1 1 eigenstate. So let me write here: a dagger when acts on 0, it will give you 0 plus 1 1. And when a acts on 0, it is basically 0. So from this relation you get 0. So it is 0. So when if you yeah, and if you go a dagger 1, you will find 1 plus 1 root 2 2. So similarly, what else you have? A dagger 1, then a1, that is basically square root 1, 1. So using them, you can now uh, write the expectation as follows. So first term you have b1 square. So again, so first when a operates on 0, that is giving, that will be basically give you 0. So then, but you have a dagger acting on 0, that will give you 1. So simply 1. So that is inner product of 0 and 1, then plus b1 b2. Similarly here you see, when a acts on 1, you will get 1, but when a dagger acts on 1, you will get 2. So so there is a mistake here. So when a acts on 1, it is square root 1 0. So so here in the second term you will get 0 0 plus 0 and 2. uh, so there will be square root square there will be square root 2 factor. Yeah, so this is your from second term. Then from third term you have b1 b2. uh, uh, you have first term will be 0, the second term will be a dagger when x on 0, that is 1. You have 1 1 plus b2 square. Then when I integrate on 1, that means 2, that means you have 2 2, uh, 1 2, then plus, uh, you will get, let me rewrite this properly. So yeah, in the last term when a acts on 1, it is uh, root 1 0, that is basically 1 0 plus square root 1 2. Yeah, so this is what you will get. Now you see which are orthogonal, you can, that will go away, and you will, so these are orthogonal steps. And since these are normalized states as said in the question, so when you take inner product of 0 0, it is basically 1. So from here you will see that only two terms will survive. So one from here, this is 0, this is 0, and also this is 0, also this is 0. So you have uh, two times of b1 b2 h bar 2m omega. So this is your expectation value of x. Yeah. Uh, so any doubts or any question from here? Uh, any question from here?
No, sir.
Uh,
Uh,
uh, there was one question. Oh, what is it? Can I connect you through LinkedIn? Why LinkedIn? Can you speak? If you want to say something, we Vishwotam.
Hello, sir.
Yeah,
Am I audible?
yeah, yeah. Fine. Yeah, go ahead.
Yeah. Yeah. I'm sorry. I don't. I'm like not very good to like. I'm not like. I'm actually a mechanical engineer.
Okay, okay.
Yeah. So I just found like I didn't actually knew the meaning of quantum or anything.
Okay, okay.
But I just found it amusing, like the double slit experiment from my 11th standard. Yeah.
Okay, okay. Yeah.
So, like out of interest, I just chose this course.
Okay, okay, okay.
Even I'm like, I'm still in the process of going through basics and trying to cope up with this.
Yeah, 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 yeah.
If I have a permission, can I connect you through LinkedIn, like to ask for
You
guidance?
you want to know some doubts or something, or
Yes, sir.
yeah, it's fine. You can email me, or also, yeah, LinkedIn is also fine. So like I can maybe uh, I like in LinkedIn. So I mean, you can search my name, or mail
Uh,
ID. I can give you my mail ID right
yes,
now.
sir. I found your LinkedIn, PMRF scholar, right, sir?
Yeah, yeah, right. Right.
Yes,
So okay, I can connect to and I will open my LinkedIn. So
yes,
if you need, like, I can paste my email right here. So here I'm
yes, sir. I'll
just
note it
putting in
down.
the uh, message box. You can mail me if you have any query.
Uh, and if I may, sir,
So, this is your basically this is your advanced quantum mechanics course. So you will expect like more new things if you are not very much familiar to quantum mechanics at all, because quantum mechanics one, the basic level course, which is generally covered during the like I mean undergraduate year of second or three. So if first I would say, like, go through some of the important topics of quantum mechanics one course, level one course, and then you can follow these topics well. I mean, you can directly also come and join these sessions and try to follow what is happening, but it would be much easier if you try to uh, pick other I mean basics, which is essential not just there in the quantum mechanics one, but very essential in this course also. So if you cover some important key ideas about what is quantum mechanics, how it works, so then you are good to go. So
uh,
you can do it. It will take a little bit of time, but it's fine. You can join this course also. No.
yes, sir. And just wanted to ask one thing. So my background is that right now I'm in like about to finish my final year.
Okay, okay.
I completed my internship in ISRO LEOS, the sensors division,
Where exactly?
Bangalore.
Okay.
ISRO LEOS,
Oh, ISRO.
space organization.
Okay,
LEOS,
okay,
the sensors division.
okay, okay.
So I wanted to know, like, me being a new to the quantum mechanics, what is the peak of applications have you seen in your
Like,
experience?
okay, so, like, if you are asking in particularly in my area, like the research, if what I'm doing, so I'm like, I initially started my research in quantum theories. So basically something related to quantum information and some related to some complexity in quantum systems. So those were some few experiences of mine personally, where I have worked on quantum theories. But quantum theory is really vast. If you want to know what are the I mean direct applications right before you see everything, every technology that you see, I mean every silicon technology also, within deep down, every single silicon chip you see, I mean there are uh, I mean, there are quantum particles. It is the mechanics of electrons and ions and all these things that make your electronics work. So, if you I mean, even inside a transistor, how there is a, I mean, how ions flow, or the charge carriers basically goes around each other. Like, it is due to some quantum mechanical phenomena called this tunneling and all these things. So quantum mechanics is a like I mean is a I mean it's not just technology, which I just said, like it is everywhere, all around the places. So I mean there are many other applications which you will find. And yeah, if you talk about material science, semiconductors, all this you will see. Um, so yeah, uh, and in particular, like you said, you are from mechanical engineering background, so you have done mostly classical theories. So
Yes.
classical theories is basically like it works well when you are a limit when for example, the Newtonian laws,
Yes.
that is what
All are
what
based and governed
classical
by the.
theory. So that works perfectly well when you are working with classical objects, the objects which is around you. But when you talk about the quantum particles or particles like electrons, photons, things are very different, very totally different. So you need a very different mechanics, like developed by many other people, starting from Schrodinger, Heisenberg, and all this. So yeah, and you'll see how exactly. Many new phenomena we uncovered because of quantum mechanics, whether it's photoelectric effect or black body uh, radiations and all that, and understanding about atom and like spectroscopy, whatever. Everything has to do with this quantum theory.
Yes.
So yeah, so yeah, it's good if you have interest, you can start. So
Yes.
yeah, yeah, what is
Because
basically.
the thing is, I can't clearly tell like what I have worked there.
Okay, okay.
But I can hint you with something that I think recently with I think DRDO,
Dear.
they did free space communication, free
Okay,
space optics.
okay, okay. Face space.
Yeah, and yeah, while reading the description, they had also told like quantum communication
Yeah, yeah. There is
written
a
with that. So
topic.
I was like in like so some mine also was something related to that as we were trying in space, but I was keen to know like what is this quantum like
Okay.
added to that. Why is it that?
Uh, yeah, yeah. So yeah, there are a lot of things. I mean, every single branch of science, if you see today, ultimately they uh, find some way using quantum mechanics through which modern science is explained. Like even in optics, which you normally do, nowadays people do quantum optics. So at the level of photon, things will change. No classical idea of optics will work there. So you have to go to the photon level to explain things. So
And
that
will
photon level, only quantum mechanics will work. So you cannot explain photons using classical theory. So likewise, even in communications, like if there is anything that deals with mechanism or some understanding at the quantum most level, then you need quantum mechanics. Even in biological systems also, like if you go to the cellular DNA level, I mean at the I mean there are things called mutations which are also again caused due to the quantum phenomena. So it happens because of some electrons or something, uh, or some due to some uh, tunneling of electron, there is a deletion of protein or something. I mean, I'm not very familiar, but uh, these are the things that comes or which are manifestations of quantum principles.
yes. So like in terms of communication, I think it can also promise us a good encryption.
Yeah, yeah, definitely.
Yes.
So yeah, I mean, try to go through some basics first, and you'll see. If you, it would be different to see how this quantum mechanics works, but it is really interesting. So just try from the basics, and then side by side you follow this course which you have registered, and you see how things will work out. And also
Yes.
there are very interesting topics in this NPTEL course which we have registered. So
Yes.
you'll find them also useful. So yeah, any doubts like you can.
And will there be live session like every week, sir, after
Yeah, yeah.
content
There's this
also?
live session you can join. So
Like, will it be every week or
yeah,
the
it's every
frequency
week.
of it?
I think this will be actually this was supposed to be last Saturday, but due to some issue from my end, so this was called off, and it was rescheduled right now, which we are currently live. But again, we will meet on Saturday from 4 p.m. So every Saturday till the end of this course, you can have these live sessions where we can interact and discuss some problems like what we were doing today, and some other doubts like what you are asking. Yeah,
Yes.
हेलो
Yes. Thank you, sir.
yeah, yeah, yeah.
इनका नाम क्या था विश्वातम
Who?
Um,
विश्वातम
Yeah.
सर
yes.
अगर आपको बेसिक क्वांटम मैकेनिक्स के मैथमेटिक्स के लिए बहुत ही सिंपल वर्ड्स में कुछ चाहिए तो मेरे पास एक बहुत अच्छा प्लेलिस्ट है। अगर आप
हाँ
अपना
हाँ
ईमेल देंगे तो वो बहुत ही बेसिक से आपको मतलब वो टीचर आपको पढ़ाएंगे बहुत बेसिक से मतलब बिल्कुल सीख सकते हैं उससे।
हाँ मैं चैट पे डाल दूँ अपना ईमेल।
हाँ
यस
मैं
यस थैंक यू।
आपको
Yeah, you
हाँ,
can
मैं आपको भेज दूंगा
drop your email.
व्हाट्सएप।
You can, like, yeah, for basics you can start with David Griffith book, which is like good to understand. It will start with a right amount of basic mathematics, and then you can follow there. And there are many other books, but let's start with David Griffith.
यस थैंक यू जज से।
Yeah.
थैंक यू सर।
Okay. Yeah. Yeah. And there was one question by someone, Hanuman. Sir, I was going to let record video is available. Yeah, yeah. This recorded video will be also available, and it will be communicated through your maybe through email from NPTEL, or you can open your NPTEL portal from there. Also, you can get a link for the recorded video. It will be saved in YouTube. So yeah, we will have that. And also, as far as I can see, we are also almost about the time. Like the time is almost up.
सर
Uh,
सर एक आखिरी क्वेश्चन।
yeah, yeah, question. Yeah,
सर आप पीएचडी कर रहे हैं सर या
yeah, yeah. I'm doing
पोस्ट
right, right.
कहाँ से सर पीएचडी कर रहे हैं?
At IIT कानपुर, IIT कानपुर में मैं स्ट्रॉन्ग ग्रेविटी में मेरा रिसर्च है, PhD.
तो सर मैं भी वहीं से करना चाहता हूँ।
Okay, so what are you doing?
अभी तो मैं बीएससी कर रहा हूँ पर थोड़ी
Okay, okay,
किस्मत खराब होने की वजह से थोड़ा मतलब रेगुलर नहीं कर पाया तो
okay, fine.
ऐसे करना
So,
पड़ता है।
yeah, it's quite a way to go. So, try to do as much your basics. Like, I mean, BSc has a lot of uh, like a lot of basics covered. If once you do that, then things will be easy for you to follow in masters. And yeah, and masters will be little bit more advanced. But yeah, but you need to be good in basics, which you are doing in BSc.
यस
Okay,
सर और एक छोटा सा डाउट है।
right.
व्हेन जब मैं आपका लिंक्डइन देख रहा था, वो प्राइम मिनिस्टर रिसर्च फेलो,
Uh,
क्या आप बता सकते हैं वो एग्जैक्टली क्या है?
Okay, so this is like it is a fellowship program. So it is run by government of India. So under this fellowship program, like you have, I mean, you because I think you are aware that if you do your PhD, you will be under some fellowship scheme through which you will be getting some fellowship amount, and yeah, that is how you what is you see in PhD. So generally, in PhD across the country, you find there are CSR who funds fellowships for research scholars in working in IITs or other institutes, and also JRF and all this. Yeah, CSF, JRF, and then. Uh, and there are other institute fellowships. So likewise, this is Prime Minister Research Fellowship. So this is a bit different fellowship where you have like I mean this is a different scheme. You can find it if you Google it. I mean,
And like I
सर
think if after completion you have to present it to them, like the government officials, or
no, I mean, it is like when you join PhD, so you will be under some fellowship scheme. So, like for example, if you have some JRF, you can like you have to appear for some CSR like you I mean net exam, there is this net entrance exam, or if you have some other fellowship program, like there are this inspire fellowship. So for that there are other eligibility, so there are different process. So through by different means you can secure a fellowship scheme under your name, and using that you can do PhD, because from there you can get your expenses and yeah.
सर एक डाउट था कि अगर आपको इस फेलोशिप मतलब ये फेलोशिप के लिए अप्लाई करना है तो मेनली क्या स्ट्रांग होना चाहिए? आपके पास ज्यादा रिसर्च पेपर्स होने चाहिए कि एकेडमिक
I mean,
एकेडमिक बैकग्राउंड?
research paper will help you better, but you need to have some good academic record, like your CGPA and all. So let me, like, I think the time is up. Let me first, uh,
ओके सर.
like, yeah, I think maybe we can talk later if you don't mind.
Yes, sir.
Actually, I also have to leave. So if you have got something I'm like going before, then please ask me, or maybe you can ask me if it is something small.